Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 24th, 2026, just 4 days ago. It introduces SymTorch, a library that automates the process of replacing deep learning components with interpretable mathematical expressions, achieving an 8.3% throughput improvement in a large language model proof of concept. The paper is titled SymTorch, a framework for symbolic distillation of deep neural networks. And as we'll see later, the potential for uncovering physical laws inside black box models is quite significant. Figure 1 illustrates the SymTorch pipeline, which converts black box layers into clear mathematical formulas. The process begins in the wrap phase, where the library attaches a monitor to a specific component within a trained architecture, such as a transformer or convolutional neural network. Next, during the distillation phase, it captures input and output data to feed the symbolic regression engine, which generates equations that approximate the layer's behavior. Finally, the output stage swaps the original neural block for the chosen symbolic equation, creating a hybrid model that is both faster to execute and easier to interpret. So while Figure 1 outlined the global pipeline, Figure 2 illustrates a local interpretation method called SLIME. On the left, we see a complex nonlinear model where the decision boundary, shown in orange, is too irregular to capture with a single equation. To explain a specific prediction, the framework focuses on a point of interest, marked with a blue cross, and samples the model's behavior in that immediate neighborhood. Then, as the right panel demonstrates, it fits a simple symbolic function, represented by the smooth blue curve, that locally approximates the complex boundary. This allows users to derive exact mathematical explanations for individual decisions without needing to simplify the entire network. Alright. Figure 3 details the specific pipeline used to accelerate transformer models by replacing their heavy MLP layers. Because symbolic regression scales poorly with high-dimensional inputs, the process starts on the left by using PCA to compress the incoming activations. These reduced features are then passed through the central symbolic model, which computes the output using a discovered mathematical formula. Finally, a second PCA step on the right expands the results back to the original dimensionality, allowing the rest of the network to continue without interruption. Well, with the pipeline established, Table 1 now quantifies the impact on model performance using perplexity. The baseline model achieves a score of 10.62. First, look at the second column. Applying just the PCA compression increases perplexity by 3.11. Crucially, the next column shows that the full SymTorch implementation adds only 3.14. Because these numbers are so close, it implies that the symbolic equations capture the compressed layer's behavior almost perfectly, meaning the performance cost comes primarily from the dimensionality reduction itself. Finally, the control column shows a much larger jump of nearly 7 points, confirming that the symbolic model is preserving critical logic. So, Figure 5 places that trade-off into context by plotting throughput against perplexity. The vertical axis shows speed in thousands of tokens per second, while the horizontal axis tracks the error rate. If you look at the purple diamond, that is the baseline QN 2.5 model. Now compare it to the blue star representing the symbolic version. Although it shifts right due to higher perplexity, it also moves up, reflecting that 8% speed boost. Importantly, it lands right next to Llama 3.2, showing that it stays competitive on the efficiency frontier. While the previous figure focused on performance metrics, Table 2 shifts to interpretability, comparing ideal mathematical rules against the actual logic Llama 3.2 learned. The middle column lists simple expected equations, but the right column reveals the model's messy internal heuristics. For instance, in the first row, instead of learning x0 plus x1, the model approximates addition using a convoluted formula with inverse functions and sine waves. This pattern holds at the bottom for temperature conversion, where it roughly fits the curve but adds 33.79 instead of 32. Wrapping up, the main takeaway is that SymTorch makes symbolic distillation practical by automating the heavy engineering work. It allows researchers to swap black box layers for clean equations, offering a powerful way to accelerate large models and uncover the physical laws hidden inside them. That's it for this episode of the AI Research Roundup. I'm Alex, thanks for listening.